So I want to welcome everybody today to the next PSDI webinar. In today's webinar, Dr. Keris Willoughby will be talking to us about open science. So I will now pass over to Keris. The floor is yours.
Thank you very much. Hello, everybody. Welcome to the webinar. So I'm Dr. Keris Willoughby. I work on the PSDI project at the University of Southampton, and I'm going to talk to you about open science today. So just to let you know, so this webinar has been adapted from learning materials that are developed by the Skills for EOS program. And so there's lots of material that's from there. You can find out more about them from the www.skillsforeos.eu website. All of these slides will be available after the webinar. So any of the links that are included in here, and there are lots of them, you'll be able to get access to. Okay, so what is open science? So open science is quite a broad concept, and it means different things to different people. But what we're going to use in this webinar is the UNESCO definition of open science, which is a set of values, principles, and practices that aim to make scientific research from all fields accessible to everybody for the benefit of the whole of humanity. And what that means is that the products of scientific research, things like research articles, data, and software, are available to everybody so that they can be used to build upon, to build new science, and to inform decisions and practices that are for the benefit of the whole of the population. Also, it's about participation. So it's not just about these things that we produce in science. It's also about giving everybody that's interested, that wants the opportunity, the chance to join in with science and engage with science practices. And we'll talk more about these things. So the open science core values are designed to sort of say about what we should be trying to achieve with open science. So quality and integrity is really important in sharing what we do, in sharing our data, in sharing our practices. Then we're helping other researchers to gain knowledge that they can build upon to do their science, but also we're encouraging and increasing the amount of trustworthiness in science. All the scientific research that we do should have a benefit for humanity. It should be open so that everybody can see and make use of that knowledge. There also should be equity and fairness in it. So it's not just about one set of people having the opportunity to have access to these materials or to take part in science. It's that everybody should have that. So whatever discipline, wherever people are from, they should have the chance to do it. And also everybody, the whole of humanity, should have access to these different pieces of scientific knowledge. And diversity, inclusiveness. So it's important that we acknowledge that there are lots of different ways of doing things. There's not one size fits all for open science. There's lots of different knowledge, lots of different practices, research generated in different languages, and people have different knowledges. And it's not just scientists that have knowledge, there's also communities have knowledge as well. So the guiding principles for open science, so they're very, very similar to the values. There's a lot of overlap in here. So it's all about making sure that there's transparency so people can look at data that's been produced, the methods that we use, and actually check that it's valid, that it's reproducible, that the conclusions that people are coming to make sense. It's also important that there are these equality of opportunities so that everybody can be involved, everyone can access the information, but they can also contribute and benefit from the science as well. So again, with trust, it's important that there's responsibility, respect, and accountability. So this is looking at making sure that the research that's done and the way that the data and the knowledge we have is used in an ethical way. And again, collaboration, participation, and inclusion. And there's no one size fits all of open science, and it's important that it's sustainable. So it's not, open science isn't just something that we want to do for a couple of years, it's something that needs to carry on for the long term so that all of these benefits can be brought to humanity. So there are four kind of pillars of open science. So the first one we've talked about is the open scientific knowledge. So this means things like publications, research data, even educational resources and software, so that everybody can have access to these things that enables them to do research, enables them to use this knowledge. There are also open science infrastructures, and these are both physical and digital. So for example, researchers need to be able to access different things in order to actually carry out their research. So with a physical thing, it could be something like a telescope or a particle accelerator or a microscope or something like that. Whereas with the digital, it's all about places where the data can be put, tools that enable us to actually make use of the data to analyze it so we can make sensible conclusions to come out of that data. And the other side of it is the people part of it. So it's engaging with other knowledge systems, the recognition that other communities, Indigenous peoples have knowledge that doesn't exist in research. For example, communities with particular health conditions are going to have a lot more knowledge about that health condition than the researchers that are potentially investigating them. And then also open engagement with society in general. It's important that society, the public, can understand the science, the research that we do, and they can get the value out of it. So why does the world need open science? So there are a lot of problems in the world. So thinking about things like health, the environment, the way that society works, there are lots of problems that need solving. And open science allows us to accelerate and innovate in order to solve these issues. So the way that the open science practices foster this innovation, so access to scientific output, and that means access as soon as possible, rather than waiting, sitting on the data and maybe the conclusions of research for years. It's important that we have that data now, we have that understanding right now, so that we can do things with it and we can build upon it. Sharing primary data rather than just the final results helps with the whole trust and increases the reproducibility. And also quite often having that primary data makes it much easier to build upon it and do other things. So what the researcher thought the data could be used for could be very different to what somebody else can do with it. But all of that use is very valuable to solving these problems. Open educational resources enables anyone to have equal access to learning and to skills and to capabilities. And this is very important, particularly looking at a worldwide activity to get people skilled up. And again, citizen science and public engagement. It's important that the public understands the value in the science, that they become more literate, and that they can get the advantages of all that research and innovation. So what does open science look like, and what are the impacts of it? So going back to one of the sort of very first sort of leaders in the whole open science is the Human Genome Project. So this is a global project where scientists were sharing their data on the human genome in order to create a map of that data. And that data was shared immediately. So it was all about getting that so that other people could build upon it and learn more. And it took 13 years to map the entire human genome. But the impacts of this have been huge. So there have been important advancements in medicine and healthcare, particularly looking at personalized healthcare. So understanding somebody's genetic makeup can help to have targeted therapies, and it can help to make sure that the side effects from drugs are less impacted based on your personal genetics. There's the researchers speak, so it's accelerated the research in genetics, the identifying different diseases and pathways to different diseases, and also developing technology. So as well as precision healthcare, there's using something called the CRISPR, which can change genes and actually create therapies that way. So there's a lot of new research, a lot of big impacts on this. So economic impact, so whole new health domains, lots of new businesses, but particularly in the scientific collaboration side of it. So because this is human genetics, it's important to discuss the different ethical concerns about this and how collecting the data needs to be looked at, and also how the data is shared and how it is used. So there's policies that didn't exist before on how you manage human data in an ethical and legal way. It's been very important for raising public awareness of human genetics, and particularly the fact that genetics are different. It's no good looking at a small subset of society and assuming that everything actually applies to them. So treatments and healthcare are much more equitable across the globe. Another example, malaria is a very significant disease across the world. About 200 million people get sick, and about 600,000 of those die each year, and most of those are children. There are problems with traditional approaches to developing drugs, particularly as the malaria parasite becomes drug resistant very quickly. So there's not the same advantages, sort of profit-driven advantages for big pharmaceutical companies to work in this area. And so a different way of working that isn't about patents and making lots of money is needed. And the big problem is a lack of innovation. So the open source malaria project was set up to try and find drugs that were effective against malaria as quickly as possible and without being focused on patents. It was all about having open discussion, open collaboration, and where all of the data was shared immediately, and not just the data. So it's an open notebook project where the notebooks were shared, the methods were shared, the data, and it meant that it was much faster to work out what are good leads, what are good potential drugs, and what are dead ends. And there's been positive results in finding more efficient ways of developing drugs and looking at potential new routes for it. And the methodology used here has also been used to look at how we can do drug discovery in other fields such as TB. So another example, this is one I only found out last week, is looking at how you can use identify molecules that can interfere with virus replication. So all of us remember COVID. It's not in a pharmaceutical company's interest to develop drugs for diseases that don't already exist, but it is also important that we can have a rapid response when such problems do occur. So this is a project that's using AI-driven and computational chemistry in order to identify these potential candidates for drug discovery. So environment and climate change is another area. So for example, across Europe and across the world, there are lots of places that are sharing data, and they're sharing it immediately. It becomes available. So looking at things like geohazards, climate change, ocean research, and so on. And then another example here, EDS books. So this is using computational open notebooks. So in this case, you can not only get access to the data and the methods, but you also have the software there. And these are all peer reviewed. So the trust in the knowledge that's being produced is very important. So what do we need to do in order to support open science? So there's a lot needs to change. The traditional way that we do science is all about writing papers. We protect our data. We don't want to share it with other people because we don't want people to come along and scoop us. We want to keep it secret. But this needs to change. This needs to be different. So policies and institutional support and the actions of different funders are needed to encourage that we share our data openly, that we do more of this sharing of what we do, working together collaboratively, doing the cross-disciplinary research where a lot of the innovation can occur, and also working with the community and communicating what we do to the public. One of the things I mentioned earlier, so the pillars of open science are these infrastructures, and these are access to instruments and also access to digital resources like software that can help us to analyze our data. And the European Open Science Cloud, EOSC, is creating a sort of a connection of these infrastructures for the whole of Europe. And in the UK Research and Innovation Organisation, so this is the biggest funder within the UK, are responsible for having access to lots of facilities and instruments, so things like particle accelerators, ships, and even satellites, and also these digital infrastructures. And this is where PSDI fits in. So across the UK, there are a variety of infrastructures for different disciplines. So there's been data centres for social science and environmental science for quite a long time. There's also infrastructures for life sciences. And in other countries, there are ones that are focused around physical sciences. And so for the UK, PSDI is filling a gap here for chemistry, materials and related disciplines, and connecting together with those other infrastructures. And so what PSDI is providing, so we're at fairly early stages, but we're already providing access to data, so quality reference data, tools that can help you to transform your data and to make it more open and easier for people to actually use and to reuse. There's also the people side of it. So we're building up a community, providing guidance and training to help skill people up and trying to get people to work together. So in order for the data that and the research that researchers are creating to work together with these infrastructures and to actually be useful to other people, then they need to be fair. So FAIR is an acronym for findable, accessible, interoperable and reusable. So looking at this at a high level, if your data and your research isn't available, if it's not put somewhere where people can access it, then it's not of any use to anybody. If it's put somewhere where they can access it, but they can't able to find it because it's not well described, then it's not very useful for anybody. It also needs to be documented. It's no good having a spreadsheet and putting it on the internet. It needs to be described so that you understand what that data actually is, where did it come from, how is it produced, and what can I do with it. And also it's extremely important, we live in a digital age where everything we do is on the computer. If we're looking for information or we're trying to manipulate some data, everything's on the computer. So what we need to produce needs to be interoperable as well. And we'll talk a little bit about these different things. But what's required around the data itself isn't very useful on its own. We need metadata, we need things that describe it. We talk about metadata as data about data, which it is, but that's not very meaningful. So what I've got here is an example. So this isn't research data, but the principles are very similar. So this is on the left there's a photograph that's stored in Flickr. So the photograph can be considered to be the data, and Flickr could be considered to be a data repository. So the photo is on the repository, but people can't find it unless it's got metadata associated with it. So on the right here shows that a lot of metadata is automatically captured by the camera when you take the picture. It's embedded in the image file, and it tells you things about the camera that took it, about the conditions, so about what the lens was, what the aperture was, what the shutter speed was, but also extra things as well. So it can talk about the software that was used, what the color profiles were, how big the picture is, where it was taken. So some cameras have GPS in them. So there's this EXIF, and this is standard metadata about photographs that's captured. And the repository can use that metadata to show you information about the picture so you can see it, but also so that you can find it. Other metadata is also produced by the repository itself. So for example, there's information about the license and about the privacy and the safety level. There's also information about how many people have viewed that image and who has liked it, who has commented on it. This is all metadata. And these are typically metadata that are captured by a computer, by some software, and put in there. But also it's possible to have user-defined data that's actually a little bit more interesting. So if you look at the photograph, you can see it's a Formula One car. But the photograph, the metadata describing the photograph doesn't give you that information. It's information that I've had to give you to tell you what it is. So who that driver is, where the track was, what the conditions were, for example, and what the event was. And although AI can do some of this work, so image recognition is very powerful now, it can sort of identify that thing. There's always some extra information that needs to be given. And this is particularly true with research data, where the context of why was it produced, what was the experiment, what was it looking for, what's actually the data, what are the materials, equipment and so on that are actually in there. Okay, so going back to the FAIR principles. So first of all, to be findable, you need this metadata. So if I wanted to look for that photograph, I wanted to look for photographs that related to it, like Sebastian Vettel driving Formula 1 car, I could type that into Flickr and it will produce those things because that metadata describes it. It's also important that it remains findable even if the place where it is changes. So if you have some data that you've put on the internet somewhere, if it moves, so websites change all the time, names of things move, servers move, you need to have something that points to it so that when everyone tries to find it, they can get at it. And the example here is a digital object identifier for a particular paper. And whenever somebody clicks on that link or uses that identifier, they will get to that data again. So it's important that the metadata and the data are linked together. I can have the metadata, but it doesn't help me if I don't have the data and vice versa. And it's also important that the data and the metadata are somewhere where they can actually be found in the first place. So putting data into a repository is ideal because that makes it findable. So accessible is about it being available. If it's not available, then it can't be looked at. If it's available in some strange format that can't be used, or it can't be accessed using a browser or using some software, it's not very helpful. And even if the data later on disappears, it's important that the metadata is still there. So there can be a variety of reasons why the data might go away. But the metadata describes what it was, how it was structured. That's very helpful to somebody trying to understand what was done later. Okay, interoperable. This is probably the most complicated one. So we talked about metadata describing things. For a machine to be able to make sense of some data that we've shared, it needs a much more complicated understanding. So it needs a knowledge representation so it can make sense of that data. So for example, if data was about Paris, the computer would need to know more about it. It would need to know that Paris was a city, that Paris was in France, what the population might be, all of these different aspects. So the metadata required needs to be linked together and to help the computer to understand it. And the reason for that is because if a computer can understand that data, they can not just display it to you, but they can also do very smart things such as combine different data sets together based on the different metadata that they might have. And then finally, to be reusable, we need to know what the data is, where it's come from, what does it mean. But it's also important that we have a license so we understand whether we can use it. If you put a spreadsheet up on the internet or any kind of data file and it doesn't have a license, nobody can use it because it's not telling them what they can do. So it's important that license is there and it explains what can and can't be done with that data. Provenance is all about where did that data come from. So we need to know who created it. If we've got questions, then we need to find out where it came from so that we can understand it and also so we can get more information. And it's important to use domain relevant community standards. So it's no good to people if the data can't be opened with software or it doesn't mean anything to them. So using community standards makes it easier for people to actually make real use of it later. So a common myth of FAIR data is that it means that the data has to be shared openly with everybody. And actually that's not true. So we have a concept of as open as possible and as closed as necessary. And the idea with that is acknowledge that it's not possible to share absolutely everything. Some information can't be shared for legal reasons because it's sensitive information or there might be sort of certain impacts. But we should still be describing that information because you can describe it without actually letting that information out there. And also it's important that we protect that data. If it shouldn't be open, then it needs to be protected. Making something open doesn't make it fair. So it doesn't mean that it's reusable. So if you don't have enough documentation, if you don't have the metadata, if you don't have the persistent identifier, then it isn't usable by somebody else. It's not going to be findable. It's not going to be reusable. So verification describes the process of taking existing data and making it fair. So if you have some data that already exists, in order to make it fair, you need to do an awful lot of work to add metadata to it, to describe it properly and to make it so that it's understandable. And this is quite complicated. What's much better is if we actually think about this process and what we need to do to make data fair, right up front at the point we're actually planning our projects. So what we need is some good data management. We need to think about how it is we're going to store our data so that it's safe, how we're going to preserve it, how we're going to describe it, what's needed, what formats are we going to use, what standards are we going to use. And the most common way of doing this is using data management plan. And the idea with this is that you do this right up front at the beginning of the project. It's quite often now a required component for grant proposals, particularly publicly funded ones, where you actually think about these things. What standards are you going to use? Where are you going to put your data? How are you going to share it later on? What software are you going to use? How are you going to go about getting that? What ethics procedures might you need to follow? So there's a lot to think about, but if you capture it right at the beginning of the project, it makes it much more likely you're going to do that, and it makes it much easier when it comes to you're actually at the point you want to share your data to make it available to people. So who are the stakeholders in science? Who's going to be influenced or can influence open science? So obviously researchers are important in this space. They're the ones that are doing the science, and they are the ones that are going to be making decisions about whether they're going to make their science open and how they're going to do it. And they need to understand and be supported by other organizations. So research institutions are very important in this process. Because they need to set the policies, they need to provide the guidance, but also they need to make sure that their researchers get properly credited and rewarded and recognised for actually making their science open to other people. Research ethics and integrity bodies are important because they are setting, again, policies. They are encouraging the transparency of the research that's being done in order to ensure that it's being done properly. Research funders are an enormously important part of this puzzle because they can make very big differences to what researchers actually do and how they share their data by mandating that they will share it and how they will do it and giving guidelines. Publishers are also the same. So at the moment, the conventions are to maybe share some data in a paper, some data in some supplementary information, but unless they actually encourage and mandate sharing in community adopted formats, in particular repositories where the data can be easily found, then people have no incentive to go about actually changing their practices. Libraries, repositories, and data centers are important as guidance and help and assistance and support for the researchers that are trying to do these things because they have the skills that are related to data stewardship and about best practices for using repositories and where data needs to end up, where the research needs to end up. And then finally, citizen scientists and the public are important to engage as well. What we need to do with all of these different stakeholders is to create this collaborative culture. It needs to be change from the way things currently are now, which is reliant upon researchers sharing their knowledge out and to actually getting more of a dialogue, more of a conversation. So this is a dialogue with the public, with citizens, but also particularly policymakers in industry and researchers together. So this idea of cross-disciplinary research and the fact that researchers should be cooperating instead of competing against each other. And the EU has got various missions to try and create policies and regulatory resources around this, but really it has to be a case that people are engaging and seeing the value of sharing these different, sharing our research with each other and being open about our practices. Okay, now we'll talk about citizen science. So citizen science is sort of a big piece of the puzzle of open science where we're actually engaging with the public. We're engaging with people who are interested in science, who want to be involved, who want to understand what's going on. So over time, science has become more and more closed as publications are kind of hidden behind paywalls, and the knowledge becomes available to just a select and elite few, and it's not open to everybody in a global way that it should be. And so citizen science provides a way to have more of that engagement. Technology has been very important in actually providing the opportunities to have this engagement. So things like websites, but smartphones in particular have been very important to provide ways that anybody globally can actually get involved in these different things. And I'll talk about a few different examples. So there's some examples here, but talk about some specifically. So to some extent, the RSPB is a really good example of a very long-running citizen science project, even though it's probably not really described as citizen science. So this is the world's largest garden wildlife survey. And this was originally started in 1979 as a one-off activity for junior members. And it was promoted by Blue Peter. And it proved to be so popular that it was repeated annually, and has only actually opened up to adults in 2001. And this year there was nearly 600,000 people took part in this activity. So this is looking at birds, recording the birds that you see in your garden. And with nearly 50 years worth of data, it's enabled scientists to be able to track long-term trends and challenges for different species. And this is a really valuable insight. Without actually opening it up to the public, it would be impossible to have access to that information. So it's really valuable. Another example along the same lines is the eBird project, which is run by Cornell Lab. And this is, again, this is an app that enables people to record the sightings of birds that they see on their phone and submit it. And this is a huge collaboration with lots of partner organizations, thousands of visual experts, and hundreds of thousands of users. And the data is made accessible immediately. So it's updated every single day. Anybody can get access to this data. And it's been extremely important in informing decisions about conservation and in research about different trends and populations, bird populations across the world. So something as simple as recording something on your phone can make a huge difference, and it can be a whole global effort. So another example, so this again is back in Europe and the UK, and this is looking at monitoring pollution, so in particular phosphate levels in fresh water. And this is using a very simple paper-based analytical device, the pad, and people that are involved in this project can collect a river sample. They can put the pad into the water, take a picture of the results, upload to the app. And this is a really effective way of collecting water across a huge geographical area and getting the results for it. And again, this is something that just wouldn't be possible without the help of the public. So finally, a chemistry-based example of citizen science, so Project M, and this was looking at a particular mineral. So this is calcium carbonate, which is found in different forms, and it's commonly used by animals in creating their shells and their bones. And it's quite interesting and important to understand how do different mixtures of other organic materials affect how these shells might form. And so this project was actually using school children. So an experiment was devised that was very simple and very safe, could be done in the classroom, and it enabled, so it used 110 schools to replicate different conditions for this experiment all on one day. So all of the data was collected on a single day for 800 samples across the UK. And the results of the crystals that were grown in the experiment were analysed using the diamond light source. So this is like a big sort of X-ray microscope. So this was real science, and the students were connecting with that real science. They were taking part in the process, so were their teachers and technicians. It was something that the researchers themselves wouldn't have been able to do without this assistance, and it gained real exposure to that scientific process. And the data was all shared, so everybody could look at the results and everybody else's results and compared what they did. So it was a really helpful for the researchers because it was helping them to do something they couldn't do, but it was also valuable for those the students and the support staff around them to actually connect with real science that's going on and understand the scientific process. Thank you very much for listening.
Very much for that, Keris. That was a very interesting talk. If anybody in the chat has any questions, please either drop them into the chat or into the Q&A, and I can read those out to Keris so we can get those answered. But while you are doing that, I've got two questions. One is a slightly more fun question, one is a slightly more serious question. Which one would you like first?
Let's have the serious question first.
Within the sort of the science community, I know that we're a very broad community. What's one thing that you think we could do sort of across the board that would improve sort of the uptake of FAIR as a principle? Like, is there something that you can think of that would elevate us towards that direction that we're really all missing?
Yeah, I mean, it is complex. So the sort of biggest challenge is the fact that, you know, making data fair is involved. It takes effort, it takes time, and it's not the primary goal of, you know, the researchers. Researchers are there to do science. They want to do that and to gain that knowledge. I think so. I think partly it's a case of tools. What we need are better tools to make that process easier. So talking about the example with the photo and AI. So AI can enable, can do automatic sort of image recognition, and it can actually identify kind of metadata and descriptions and apply those to things. So that can support so that users don't necessarily need to do all of it. So for it would be helpful if we could have tools that were able to collect a lot of that sort of describing metadata from things, because we put, so for example, in the data management plan or our proposals, we put a lot of information down about what it is we're doing, why we're doing it, what we're trying to find out. And at the moment, that's in a form and it sits on a hard drive. It's like if we could kind of combine information from different sources, then maybe that we could collect it together and actually use it as a useful description then to go with the data on the repository to kind of explain why it's there. So I think tools is a part of it. Another part of it is explaining why it's important, how it's valuable. So another problem that you get is researchers go, well, it's my data, it doesn't mean anything to anybody else, I can't see how anyone else would use it. And it's like, it's the wrong way of thinking about it. We need to think about, well, so you might not be able to see how else it could be used, but for somebody else, you know, if they have access to it, they can do something useful for it. There was a phrase that was used at the London Labs Live a couple of weeks ago, which was about data being the banana. Very strange phrase, but the idea that, you know, to me, it's a banana, but to somebody else, it's a smoothie. To somebody else, it's a banoffee pie. It's like your data has more value than you think it does for other people out there. So yeah, I think it's kind of we need to sort of get the message across, but also we need to make it easier. We just need to make it a lot easier.
One from the chat: how can misconceptions that open is equal to fair be disrupted? Yes,
I think it's probably telling more stories, because the story, so for example, the examples that I talked about where, you know, where the data is openly shared, there's no worries about, you know, that any of that data is sensitive and is problematic. I think we need to share more examples of where data is being used, but it isn't being openly shared. So one of the things is that there's a difference. If I have a data set that has personal healthcare data in it, then I can't share that openly because it has personal data. But that's not to say that somebody else can't take that data and use it, so long as they have gone through the same ethical processes, you know, that I have for some reason, but they still need to know that data exists, so that everybody, I guess it's getting that message that actually the metadata is to some extent more important than the data. But yeah, that's certainly a challenging task, I think.
So how will we enable and cover the infrastructural cost for open data to ensure long-term maintenance support of open data? Any thoughts?
I believe that would be the problem of the UKRI. Yes, so that is I mean, this is a sustainability thing, is how do you keep it? Because there are repositories that pop up and people put their data in there and they have expectations that that data is still going to be in there 10, 20, 50 years time, and then it goes away because the funding has gone away. I think that is a problem for the funders, so UKRI and EOSC as well, so the whole of Europe, and probably we'll try not to worry too much about what's going on in America. But yeah, it's a problem for the global, and it does cost money. These things cost money, and the more data and the more people that buy into this. So, we want researchers to share. We also need to think about what they're sharing. So you don't necessarily need to share everything. If you're sharing your raw data, then you probably don't need to share the intermediate stages if you are describing what it is you have done to your data in order for somebody else to make use of that and to replicate your results. But yeah, it's very much a challenge. Some data is enormous. That is a huge challenge.
So thanking you for the talk and excellent coverage of the whole topic. But the mention of industry was without detail. Industry is the most successful at tackling consumer immediate needs and also long-term challenges. Do you have any examples of industries benefit from open science?
I do not have any specific examples. I am sure that they are out there, but yeah, that's, I'm afraid, beyond what I know.
How do we move open, fair, etc., from being extra work to being a default expected behavior? Humans are lazy when it comes to this sort of stuff, especially if somebody else can do it for us. So where do you suggest that we apply the nudge?
So I think it has to come from both funders and I think from publishers. So unless things change dramatically in that publications become less relevant than the publishers. So an observation I have is that although publishers are strongly encouraging people to share their data and to use standard formats and to use repositories, they're not mandating them. And also when you go through the manuscript submission process, that is still geared up to PDFs. It's still encouraging you to put your data into a PDF supplementary file. And the process of submitting your publication and your data to go with your publication, it needs to be changed such that it facilitates those flows. It's telling you where you should be putting your data, what extra information needs to go with your data, and it needs to be encouraging that, and it needs to get away from this. It's acceptable to use supplementary information in that way. But yeah, I think we need to go, have strong words with the publishers so that they sort that out. As I say, there's encouragement, but that's not enough. It needs to be done properly. And again, tools, there's lots of information that are put into that submission process, which is metadata. It's descriptions of what your data is. That could be used to help facilitate that.
What sort of quality indicators do we have that tell us about the quality of open science? E.g., we have R factor for X-ray data, the B factor for proteins.
I think that analysing, so there is work looking at how fair things are, but also it's kind of like moving goalposts. So something that meets requirements today, the requirements are kind of going to change. But yeah, I don't know of anything specifically at the moment.
And I think that's all the questions from the chat. So I'll ask my last quick one before wrapping us up. What citizen science project would you like to see done?
So I'm very interested in genealogy and family history, and I'd like a lot more people to get their genes tested to find out more about certain aspects of that. But so that's a little bit invasive. So yeah. I don't know. I'm very much in favour of the birds and the wildlife and the plants and all of that kind of thing. So, but yeah, it's all good. There's so many interesting projects. You could spend your life just doing citizen science projects, and they'd be really exciting and fun.
So thank you, Keris, again for a really interesting talk on open science. I have a couple of quick things to say about PSDI. Before we leave. So PSDI now has a veritable collection of resources over our website at psdi.ac.uk that sort of went live officially for the first time last month. So we'd be really grateful if you could go and check that out for us. I believe there is a link to send some feedback. So if you think there's anything that's missing or anything that we can change for the better, we'd really appreciate the feedback to that. We have a couple of events coming up. We have a data curation roadshow that we're doing alongside the DCC, one on the 25th of June in Cambridge and one on the 9th of July in Southampton. We'll be hosting PSDI in-person showcase in Birmingham, so do keep your eyes out for further information of those via the website, by our social media, or by our mailing list, which is probably one of the better ways of keeping in contact with some of these things currently. Thank you all for coming to this webinar. Thank you again to Keris for presenting. And I hope that you enjoy the rest of this Thursday afternoon.